Thanks for joining. Today is day number 10 and we are going to learn about IP connectivity. You can see that overall weightage is 25% and the topics that we have, so topic listed here, that understand that what is the routing table, what are the key components of routing table, how routers build their routing table. We have to go and create some routing as well. Some routing means that we have to go and do some labs where we have to configure the static routing, and then we have to perform lab related to OSPF version 2 as well. Within OSPF, we have to understand different terminologies like the adjacency, point-to-point network, broadcast network, and finally we have described the purpose of function and concept of first hop redundancy protocol. This is FHRP that we'll see later on in this section. So I have splitted this within different days. Today we are going to learn these topics. So day number 10, you can see that we are going to learn about routing protocol. Within routing protocol, what does it mean by prefix, subnet mask, next hop, AD value, metric, and gateway of last resort? What does it mean? All these topics we have today. So today we are going to discuss about 3.1a up to G. Now you can see the update in the topology. So far we are working on the switching network where we have switch 110, 101 and 102. Now these switches, so these are nothing but your LAN, your campus network. This is your LAN network. But these switches, they are connected with some sort of edge routers. Edge routers or core routers, you can think as. So here we have two new routers, router 11 and router 12. They have the connectivity like this. You can see back-to-back connectivity, and we have the full mesh type of connectivity with the switches. Again, router number 12 is connected back-to-back with the switches. And then you will see that this router 11 is connected with ISP as well, right? So here you can see that R3, as I mentioned here R3, but this is the ISP router. That means that suppose your internal network, it has to go outside, then it can go outside like this, means in this direction, or even it can go outside via this direction as well. So I have created one exit point here for our network. Either the network can go via router 11 or it can go via router 12. But since we don't have any connectivity like this, so from router 12 also it will go to router 11 and then ISP. Okay, so this is the updated overall topology we have. In this section, we are going to use this topology, and you will see the interfaces as well. So since these are the routers, right? Router 11 and router 12, that means that will go to these interfaces and we have to assign IP addresses. We have to go to these interfaces and we have to assign IP addresses. At the moment, we will not use this link, but we can use it in the next section when we have OSPF. So I will utilize this link as well. So you will see the redundancy, and I will update the interfaces name as well. Suppose this is actually this is E01, 02 and 03. This is E01, 02 and 03. Like that we have the topology. Right. So with respect to this updated topology, let's try to understand the routing protocol code, prefix, subnet mask, and all these things. Later on, we'll go and log into these devices. We'll assign the IP addresses and we'll try to simulate a lab practice. Let's go on. Let's move on. So now you'll see that you can go and assign the IP addresses as well in the switches, switch 101. Switch 101, here you can see switch 101. Yeah, here it is connected like this. So switch 101, you can go and you can see that we have VLAN 10 and 20 and 30, etc. So I can go and use for VLAN 10, I can go and use 10 network. the connectivity from 101 to router 11, I can go and use 1.0. So here you will see that here I can go use 1.0. So 1.0 network from here, and these interfaces are trunk. That means these are layer 2 as per our lab. We can go and simulate lab like this. This is 1.0. And here also we'll go and assign some IP address. We'll see that. So we are going to use this particular section to simulate our lab. Let's see. Okay. So router 11, you can see that we can go and assign 1.1 and router 2. So router number 1, 2 or 2. So either, yeah, 11 and 12. So here the IP will be 2.1. We will see that. Here the IP is 1.1. And then you have IP here in this interface. We are not going to use this IP because we don't have router 12 connected to ISP. But here I have added this IP address, but we don't have that. Anyways, let's move on. Then switch 102, you can see the network for VLAN 10. Switch 102 connected with 2.2 and then trunk. Then switch 110, the VLAN 10 and 20, and then ISP like this. So this is the IP schema that we are going to use. With this IP schema, we will perform the lab as well. This is a detailed IP table. You can see that we are going to perform in the lab task. Let's understand these things one by one. So first of all, we have the concepts of routing table. What is routing table? You know what is routing table? Give me the definition for routing table. What is routing table?
Mm, a list of routes that you can have.
The routing table, so let's go one step back and understand the routing table first. So what is happening? Say if I go here to these routers and if I assign some IP 192.168, suppose this is 1.0/24. 1.0 is what? This is the network address, right? And I can go and assign IP 192.168.2.0/24. And here we have some 203, some IP, some ISP IP. Let me quickly check that what IP we have. 203.0.1.1.3. Okay. Here I will go and assign IP. Say 203.0.1.1.3.0/30. Let me confirm. 203 203.0.1.1.3. Okay. So now you can see the IP addresses, and here over the VLAN, what IP addresses we are using. So over the VLAN, the IP addresses that we are using for VLAN 10, I'll go and use 192.168.10.0/24. And for VLAN 20, suppose we have two VLAN. So that means that this host that we have, this host may have IP 192.168.10. For example, 100/24, and the gateway will be 192.168.10. Oops, 168.10. Suppose 1 is the gateway address. So suppose if this host that we have, suppose it has to go, this host has to go and use the internet. How it will go and use the internet? How it will reach? So first of all, it will check its IP. And suppose it has, this host has to go and use internet, and internet IP is, for example, internet IP 200.113.2. This is the internet IP that it has to go and access, right? So you can see that where it is. It is in 10 network, right? 192.168, 192.168, 10.100. From here, it has to go and use this network. It has to reach here to ISP. Then only it will go and use internet, right? Or any other net. So first of all, it will do check that this 203 is in my network. So it will do some sort of ANDing process to reach to its gateway. First of all, it will go and reach to 10.1. So where is 10.1 we have defined? We have defined 10.1, suppose to this switch. This switch we have defined 10.1 because this switch we have 20.1 as well. Because suppose, now you think like this PC, let's understand everything related to this. 192.168, suppose its IP is 20.100/24 and its gateway 192.168.20.1, right? So there are two parts here. First part is that if this PC has to communicate to this PC, right? Even we have three parts here, not two, we have three parts. So suppose there is one more PC in the same VLAN whose IP is 192.168, 10 dot suppose 99. His IP is 10.100, other PC IP is 10.99. That is part of same VLAN, right? Part of same VLAN. So within same VLAN, the communication will happen. Within different VLANs, communication will happen. And then finally, it has to go outside to use the internet, right? So within same VLAN, who will allow to do the communication within same VLAN with help of this access switch? Because that particular PC is also connected with some other interface. So within same VLAN, they can go and do the communication because source will be its address, destination will this address, and switch knows what is the source and destination. So the communication will happen at the switch level. Now suppose if 10.100 has to reach to 20.100, then switch will tell, the switch will tell, see, none of my interfaces having 20 network, then you should go and reach to gateway. Then in this case, it will come to switch 101. Actually, what it will do, it will flood all the interfaces with broadcast messages, and that request will come to switch 101, right? And then switch 101 will tell, oh, I am a switch, I can do router in a stick that I can provide you inter-VLAN routing. So switch the IP 10.100 can reach to 20.100. So communication will happen like this. It will come here, it will get the address and it will redirect towards the other PC. So you can see two-way communication, two communications so far, local communication here within the switch, and even the local communication, but with respect to layer 3 switch where you had to find the gateways for the VLAN. But what will happen if the destination, so source will be this IP and destination you have with this particular IP. So in that case, this switch will tell, oh, that I don't know how to reach to 203. I can go to my gateway. So now it will go and send the query packet to the router. See, this is the network that is not part of my database. And since I have some static route, later on we'll go and create some static route to this, that how this particular layer 3 switch can reach out to the gateway, how this particular switch can go out from its network to the provided network, to the provided gateway network, that we can go and create the static routing or dynamic routing. So the packet will come here, he don't know the destination, then it will get flooded, it will reach to the gateway, first gateway. Here again it don't have the information, but since in its routing table you have created the route that okay, anything that I don't know, anything that is unknown, send to this router. Now the packet will come to this router. Router knows that how to reach to the ISP. Then it will forward that packet to the ISP. Here, since this is the private network, 192 is what? Private IPv4 address, and 203 is what? Public IPv4 address. Since this is a private network and you want to move to the public network, so here we will go and perform some sort of network address translation, NAT. So we'll do the NAT. So the internal IPs will get converted to the external IPs and it will reach to the destination. Right. So here again, the question here is this, so what's the use of routing table here, and how the routing table will help us to reach out to the destination? Yes, so we will go and create the, we have option, we can go and create the static routing table, or we can create dynamic routing table with dynamic protocols such as OSPF, EIGRP, etc. So automatically they will build the routing table. Routing table is nothing but the best path. Routing table definition is, routing table means best path to reach to destination network, right? So that means that to reach out to this ISP, you may have multiple paths. You may go like this, or you may go like this. But which is the optimal path? This is the optimal path because here you have less number of hops, less number of devices to touch. You can go like this also. You can go like this also. But these are less preferred path because number of routers, number of links are more, right? So this will be the best preferred path. So that means when you create dynamic routing protocol to build the routing table, then it will show you this particular path. Why? Because this is the preferred path, because this is the best path to reach to the destination network. Correct? So that's the thing, that's the routing table definition. To build the best path to reach to the destination network with different type of algorithms that we will discuss later on. So let's go and check the routing protocol code. Routing protocol code. So first of all, a routing table is a data table stored in a router or a network computer that lists the routes to particular network destination. This is the best route to the particular destination network. Components of routing table are routing protocol code. So if you go and check the routing table, show IP route, what you will see? You can see these codes. C stand for connected, then a static route, then RIP route, OSPF, D stand for EIGRP, B for BGP. These are the code. What's the significance of these code? You will see later on the significance of this code. But let's go step by step. Then you can see the prefix, then you can see the net mask, then you can see the next hop, right? So before going there, let's go here. Let me pull server here. You can see I have router number switch 101. Okay, let's go to switch 101 and we have the topology as well. So switch 101, in switch 101, interface E0/0, I can go and assign IP address 192.168.1. This is one network, 101.252. No shut. And VLAN 10 and 20. 168.10. For example, 10.1 is the gateway address for the VLAN. No shut, and interface VLAN 20, and for 20, just assigning the IP addresses. See the IP addresses that we have 10, 20, and then we have 1.1, 1.101. Because on router number 11, I can go to E0/3 that is connected IP address 192.168.1.11 because it's router 11. So I'm assigning IP.11 in the last octet just to memorize. that this IP belongs to router 11. And if I ping 192.168.1.101, that's switch 101. So if the ping will reach, that means that we have the connectivity working fine. Likewise, I can go to the ISP facing interface, that is E0/0. And here I'll give IP 203.0.113.1, 255.255.255.252. And likewise, I can go to the ISP router, that is router number 3 is my ISP. Here I have interface E0/1, and over this interface, I can go and assign the IP address to 255.255.255.252. Why we are using 252? Because it will give you only two IP, dot 1 and dot 2. And then we can go and ping just to see that ISP is reachable or not. So ISP is reachable. What we are doing basically, that from switch 101, we can reach to router 11, and from router 11, we can reach to the ISP. But this doesn't mean that if you can go to the switch and try to reach to the ISP, you will reach it. Even you can go to the switch and try to reach to the router interface. Let's see. This is the router 11. Router 11 external interface IP address. You are unable to reach, right? We'll check those things. Now what I'm telling, if you go and check do show IP route, you can see the protocol code C4 connected routes, L4 link. See in this size, and let me show this. So show IP route. Now you can see the codes here connected, local route, connect, because we are not running any dynamic or a static routing protocol. So you can see only C and L here, right? So that is one of the thing. But suppose if I go to switch number 101, if I create one IP route, I want to reach where? 203.0.113.0, right? Whose subnet mask is what? From 190 to 168. What is my gateway 1.2? Show IP route. Just wanted to show you this, that now you can see that there is one code generated. What this code is telling, that if you want to reach to this particular network, you can go via this particular gateway. Now if I try to ping, this IP, this is the IP I have over the router. And if I try to ping, still is not working because I need to create one backup route as well. So let's see, do show IP interface. 203 should be there. 203.0.113. So if I go here and if I see 203.0, okay, so I'll explain you. The ping will work. I have to create a reverse route as well. But with respect to this item, let's try to understand the theory first. Then I'll show you that how we can go and ping. So coming back here, you can see the prefix. What is that prefix? Prefix is the network address portion of the route. You can see this is the prefix. And if I create that a static route, prefix means that is your destination prefix. Then subnet mask. So if you see here, the subnet mask /24, and this is the subnet mask. It may be your destination subnet mask where you want to reach. So if you see here, the statement that I have created, IP route, see, In this statement, what I have done, this is the destination prefix I want to reach. This is the subnet I want to reach, right? And this is the next hop I want to reach. So these are the important things we have as the building block of the routing, as the building block of the routing table, that destination prefix, destination subnet, and the next hop for the destination. Then you will see the administrative distance. This is also very important, and this is something that will be utilized to prefer choose one route versus other route. So I am going to explain you this in the upcoming slide. We have dedicated slide for that. But AD distance, what is this? AD distance is the measure of the trustworthiness of the route source, with lower values are more trusted. What does it mean? I will explain you, but this is nothing but the trustworthiness. Trustworthiness means that if something is coming with lower AD value, it will be trusted more. And if you see, I should have the list of the AD values in somewhere. Yeah, here I have that. The list of the AD values, you can see the list of the AD values. Directly connected route ADs 0, static route AD 1, EIGRP 90, OSPF 110, RIP 120. So suppose if 1.0 will come with static and will come with EIGRP, which particular route the router will learn? The router will go and learn static route, that particular route via the static route, because it is coming with AD value 1, right? So what I'm telling here, that this network that a router wants to learn, it is coming with, this is nothing but the static route. So this network you are putting there as a static route. So what is the AD value for this route? The AD value you can see 1. You can see this one is what? This one is nothing but the AD value. This one is the AD value. So a router, if it will get this route via OSPF and via a static route, OSPF AD value is 110, right? 110. And the static route AD value is 1. So which particular routing protocol it will select to learn the route? Obviously 1, because it is more trustworthiness is more. It is more trusted. Why? Because its AD value is 1. If it is coming with 110, obviously 1 will be preferred. That's the importance of administrative distance. We'll see that. Let's go back to the list that we have here, right? So AD value. Example, you can see that we have AD value for static route 0. Static is 1 actually. Static is 1, connected is 0. 90 for EIGRP, 110 for OSPF. So trustworthiness will be more with lower AD value. Likewise, you have the metric value. Metric value is something which is changing. Which is changing with what? Which is changing with the protocol. So here you will see 0, 1, and after that you can see 0. 0 is nothing but the metric value. Again, the metric value is also something which is lower is better. So metric value for RIP is hop count, number of routers. For OSPF is cost. Lower cost will be preferred. A lower number of hop counts will be preferred. EIGRP having very complicated matrix value that depends upon bandwidth, delay, load, reliability, MTU, like that. So metric value is also something which is lower is better. So what does it mean? It means that suppose if we are running OSPF in our topology, and uh, this particular switch is running OSPF and it has to learn ISP network. So it can learn via this path, or it can learn via this path. But this path, if path cost is 2, say 2 here and 2 here, and 2 here and 2 here. So you will see the path cost. The path cost here will be 2. here will be 2. Suppose all the link having path cost 2. So this direction, the path cost will be 2 plus 2, how much? 4. This direction, the path cost will be how much? 2 plus 2 plus 2,
6.
6. So that means this will be preferred. Why? Because it has the lower metric. Likewise, in terms of RIP, suppose you are running RIP. So this direction, how many routers it has to touch? 1 and 2. Two routers or two hops. Here, how many hops or routers you have? Only one hop. So this will be preferred path. So likewise, routers, they are checking the what they are checking. They are checking the AD values, the trustworthiness. It will trust more to connected, then a static, then EIGRP, then OSPF, then RIP, then unknown routes. And then it will go and check the metric, metric value, like, lower med, lower AD, lower med. They are preferred. The next topic you can see here is the gateway of last resort. Gateway of last resort is nothing but where is your gateway defined, how you can go and reach out to the ISP. The gateway of last resort is the gateway is the default route used when no specific route is found in the routing table. If you do not have any specific route, then gateway of last resort will come into the picture. Now here you can see one example related to OSPF. Show IP route. If you do show IP route, you can see the protocol code. You can see the destination network. You can see the destination subnet mask or CIDR. You can see the AD value. You can see the metric value, and you can see the gateway and the gateway interface. So 1, 2, 3, 4, 5, 6, 7. In one line item, you have 7 different things to understand. The use of protocol, the destination network that you are learning, the subnet mask or CIDR, the AD value, the metric value, the gateway, and the gateway interface. All these things are used to build your routing table. This is one of the entry within the routing table database. And then the explanation is what is this? What is this? I already explained to you. Right. So knowing this fact, why not let's go and configure our devices, right? Configure our devices and check this. So what I will do that I will go and use the static routing protocol, because anyways you have to learn OSPF in the next session. So we'll go and try to perform one lab task with respect to the static route. What we will do in our topology, that the topology that we have, we will go and configure the static route, right? And then once we'll go and configure the static route, we'll go and learn these important things. So 3.2, what it is telling that this is very important. We should know this. 3.2, how routers make forwarding decision. How router will go and select one path with respect to other path. So routers, they are in their algorithm, in their protocol, they have some algorithm where they are checking the longest prefix match, the AD value, and the metric value. These three things they are checking first to build their routing table. So let's understand these things one by one. First of all, router, they can go and take the decision that they will go and put certain network in their network. The first thing they are matching is the longest prefix match. So here you can see in the example that if a router is getting 1.0/24 network from somewhere, one you can see 1.128/2025 from other interface. So when a router has to send some packet destined to this net, see here in this network, obviously you have 1.2. So here you see, check one example. Suppose if router has to send one packet to 1.130, 130, 130, 130, right? So 130 will be part of this network, and that will be the part of this network also, right? If I go and create number of hosts, with this network, how many number of hosts we have? 192, 168. 1.1 up to 192.168.1.1254, right? How many hosts do you have? This many hosts. From here, how many hosts do you have with this network? 192.168.1.129. You have to add 64 into this. 64 means 192.168.1.254. I think if you add 64, this thing will come. Or maybe if I add 64, this means what? This means 128. So if you add 128 plus 128, 200 or 24, yeah, something like this will come. So here you see that from this network you have these many hosts, from this network you have these many hosts, and you will see that you have 130. So in this also you have 130 somewhere in between, and from here also you have 130 after 1 to 8. So host will start from 1 to 9, and then you have dot 130, right? So both the network you have 130, and router want to send packet to 130. So which particular network router will send this packet? Which particular routing entry router will use this? Why? Because it has the more specific CIDR value. In other words, you can say that it has the longer prefix. 25 is more than 24. That means the router has to scan less number of hosts. Here, how many hosts router will scan? Only 128. Here, how many hosts it will scan? 250,
254.
254, right? Here 126 to be more specific. So 126 host scanning is less CPU intensive. So that's why router will use this network to forward the packet. So that means when router they are taking the decision, they are checking the longest prefix match, right? Then what is the next in the line? Next in the line we already know is the AD. Router will learn the routes in this order from top to bottom. First, it will prefer the directly connected, then a static, then EIGRP, then OSPF, and then the RIP that we already know. Then router will prefer the metric value. Suppose in one path, the path cost is 10, other path cost is 20. So router will go and prefer the path with has less cost, that is 10. So R11 will prefer route 1 because it has the lower metric, that is 10. This will be preferred. So within a routing entry, if you see the routing entry here, you have some destination network, and you can see the AD value, you can see the metric value. The first item is the administrative distance, the trustworthiness. The second item is what? The second item is nothing but the metric value. So it will check first of all the longer prefix, then the trustworthiness, the AD value, then the metric value, and according to that it will forward the packet to the destination. So first it will check the longest prefix match, then the administrative distance, then the metric. These are the three things upon which routers they are building the routing table, right? And these are the summary and all those things. So that's only we have to study in day number 10. Your task is to understand whatever we have studied today is actually very interesting. That's why I have touched very few topics just to make sure that you understand all these things. And anyways, we are going to perform the lab as well. I will show in the lab as well. But you should understand all those things that we are doing here. So let's go and try to simulate these things in a lab. So we are assigning some IP addresses. Switch 101, which is connected to router 11, which is connected to ISP R3. And let's go and create one static route from R11 to the destination. This is the default. 20113.1. Oops. and we are trying to ping. We want to reach to 203.0.113.1. This is the router address. And
That
then,
is the last resort gateway.
yeah, so let's see uh, this one, where it is connected to 101. So you can just show IP route. Let's see. So see, last resort is not set. We haven't provided
Okay.
any you know, default route in 101. Although I have created default route here to router number 11. So if it will not get a specific route to reach to the ISP, it will use this address. So let's see see, now you can see this is the last resort. Why? Because we have created the default route pointing towards this one to the ISP. So last resort I have set here on router number 11. So router number 11 obviously will reach to anyway, this is the direct connection to you will reach, but from router 11 you are able to reach somehow. If I do something here, see, debug IP packets. If I go and ping, see, so 101 source destination, see the this is multicast address, and you will see that destination again, some IP in their destination, some multicast things are going on, but somehow the router 11 is not knowing that how to return the packet to the switch number 101, right? Or maybe the ISP don't know how to reach to switch number 101. So I can go to ISP. Let's see. Let's try to create the return traffic 192.168.1.0, right? And what's the gateway? How to reach there? 203.0.113.1, right? From ISP, right? So let's go and not from this router. Let's go to the ISP here. Yeah, IP route. Yeah, from here 192.168.1.0 network, which having subnet mask of this and 113.1. Yeah. So now the ISP knows that how to reach to 1.0 network, and let's try to ping from 1.0 network. Let's see where it is reaching. So if I go ping 1.11, that's the router number 11, and then 101. Okay, so you can see here that somehow routing is not happening. We'll try to fix it. Let's see, 101 show IP route. And you can see the problem with the static route. When you are creating the manual routes, we have 3 routers. And these 3 routers, this is nothing but switch 101. This is your router number 11, and this is your ISP router R3, right? So these 3 routers, and you will see the network here as well, directly connected interfaces 192.168.1.0 and then 203.0.113.0/30. So what we want actually, we want to reach from here to here, right? And then from here to here. So when you are creating a static route, actually you have to create a static route from here to here, something like, forcefully you are sending the routes. If I have some dynamic route, there is no problem. We can do it. But since we have to create a static route, so we have to create the static route point to point. So if I go to the switch 101 and if I check my static route, IP route, and if you try to reach to the router gateways, say we are reaching 1.1. Wow. Sorry, not, oh, that's why I can see the gateway is not correct, right? Where we are reaching 1.11, right? So that means this complete IP route is wrong, but anyways, no problem. This is the route. So we are reaching to 1.1, and then if you're pinging, so we are building the path to reach to the ISP. So now you can see, let me show you this, show IP route, or maybe like this, show run section IP route. So now you can see that we have two different static route, and I am able to reach to router number 11. No doubt on that. Router 11 is reachable. But my goal is to reach to this IPC, 203.113.2. And if I do the trace route, you see it is going to router number 11, and then it is going to ISP router 2. So understand this logic here. The logic here is this, that forcefully I am sending routes to, means I have path to reach to router number 11, and then I have created path to reach to ISP as well, and I have created the backup path as well. So if I go to router number 11, if you check here, sure, section IP route. Oops, not route, I should do IP route. IP. So you will see here that I have created this default type of gateway of last resort route. So anything that will come to router 11, it will reach to ISP. Like that, I have created this, right? And what I have done, just to make sure that I am able to reach to my next hop interface, I'm able to ping here, undebug all. So from router 11 to ISP, I don't have any problem. Even if I go to ISP, IP route, from ISP, you'll see that there also I have created some static route. It will come, right, to reach to 1.0 network. 1.0 network is where? In between switch 101 and 11. So I have all the paths to go from A to B and return from B to A. And that's why you can see that this is working now, that we can reach to the ISP. But this is not the good way to configure it, because over the router number, let me go and, oops, let me go and clean the, over the router number 11, I should not have some static route pointing to the ISP. That will be security breach. Rather than, we should go and create NAT. So later on we'll go and do network address translation. So my private addresses should be converted to the public address you reach to the ISP.
Okay.
right?
Okay.
So
Okay.
we should not create some static route and all. If it is a firewall, then I can understand that we can go and create the default route towards the ISP. But generally over the routers, we are not doing such type of configuration. We should send this traffic to the firewall and firewall will take decision, or we should do some sort of NAT to go outside. Okay. So this is the topic for today's session. If you have any question, please feel free to ask. Thanks for joining. You can see that we are in day number 11, and today, first of all, we have to understand this static routing concepts, and after that we have topic related to OSPF. We have our topology that we have seen in our previous session. Let me quickly show you that topology, and in that topology we will go and enable the OSPF. Not only OSPF, but you can go and practice EIGRP, you can go practice the static routes and all those things. Even in later classes, with the same topology, we'll go and learn the BGP as well. So let's go back and let's check the concepts related to a static route. Although we have created the static and default routes in our previous session, but today we'll go and discuss more about that. So here you can see the topics we have, that in a static route, you can create a default route, you can create a network route, you can create host route, you can create floating static route. I mean, in the static route, in manual route, you have these four options, right? So before going to the theory, if I can go here and give the examples, a default route means that you have a known destination, you don't know where is the destination, then you will go and create one manual entry like 0000000. So your destination, this is what your destination network, this is what your destination prefix or subnet, and then finally you are giving the gateway from where you want to exit. So the third item here is the gateway. For example, 10.1.1.1, from this gateway I want to go outside. Now, what this concept will do, that first of all, it will try to search the destination with the routing protocols, with the exact matches, with the exact static statements, static route statement. If it will not get, then it will go and try to match this default statement. That's the idea. Suppose if you have to go and create manual static entry, suppose you have to reach to 10.10.10.0 and whose subnet mask is this, and then gateway is suppose 10.1 or 10.2, like that. So this is what, this is your network route. You are giving a specific destination network, destination subnet, and the gateway to reach to certain destinations. Now suppose in case that you have servers in the infrastructure, those servers are very important, and for those servers you want to create the individual route. Individual route means the route that is pointing towards one of the destinations. So then you can go and give like this. Suppose 10.10.10.100 is my server IP, and since this is server, since this is one IP, so you will use /32 or 255.255.255.255 as a destination network, and then you can specify the gateway. So for example, 10.100 or maybe 10.1 is the gateway. This is host specific route. You have one individual route, and then you are defining the IP routing statement, right? So you can see that all these three examples that you can see here, they are almost the same, almost the same, almost the same. This is default, this is network specific, and this is something host specific, means it is pointing towards one IP. One IP, how to reach to that particular IP, and for that you are creating the host route. Now, what is the concept about floating static? Floating static, as we have discussed earlier, that when routers they are building the routing table, they are checking the AD value. AD value is what? This is nothing but the trustworthiness for different routing protocols, that if you are learning the same network with AD90, and then you are learning the same network, routers learning the same network with AD110, which will be preferred? We have discussed about this thing, that lower AD value having high trust value. Lower AD value means EIGRP having AD value of 90 and OSPF having AD value of 110. So if you are learning the same network via EIGRP, via OSPF, then you will go prefer the EIGRP because its trustworthiness is more. Now, there may be use cases that you want to use the concept related to floating static. That means, although you have some dynamic routing protocol and your network, your routing table is built upon those dynamic protocol, but what will happen if due to some issue these protocols will get failed? So on those cases, we are creating some sort of backup routes with floating static. So the example for floating static will be, for example, I want to reach to 10.10.0 network with subnet 255.255.255.0, and then I will give the gateway as well. So I can go and give the gateway, for example, 10.1.10.2, but here we'll give the more AD value. We know that AD value lie between 0 to 255, but here I'll go and give the AD value of 200. So that means that if you are reaching to this destination network via OSPF or EIGRP, if these protocol will get failed, if something will happen with these protocols, then it will go and prefer this static entry. Why? Because its AD value is 200, and via this path it will try to reach to the destination. So sometimes it is referred as a backup path as well. The strategy in a network to create the backup path. That's nothing but the floating static. Right. So these are the concepts we have. Although these are pointing towards one concept, that means that how to create a static route and apply it. But a static route, you can think that these are the different use cases related to a static route. You can create default, you can have the network, you may have the host, you may have the floating static. Now these type of routes you can not only create with respect to IPv4, you can create with respect to IPv6 as well. So let's see, this is the IP schema, IPv4 schema, then IPv6 schema. In our lab you can use those schemas. Default IPv4 route 0000, and then the next hop. Default IPv6 route, everything is 0, so ::/0, and then you are pointing towards the gateway. The next hop, show IP route, show IPv6 route will give you the information about this. Then network route, you want to reach to 2.0. Yes, I want to reach to 2.0. Then you can give the network subnet mask, and then the next hop. Likewise, IPv6, you want to reach to this particular network. So you can see it's like in IPv6, you are giving the network information plus the subnet mask statement with same. So this is your network slash subnet mask, and then the gateway information. So this is your network route in IPv6. Then host route, specific individual IP you want to reach. So a specific IP with subnet mask slash 32. This is 255.255.255 means slash 32. And then you can see the gateway. Likewise, the same thing you will see here with IPv6 slash 128. That means the host route and then the gateway. Easy, a straightforward analogy. And then finally, you will see the concept of floating static, where you will give the static route. So this is nothing but your network static route. This is nothing but your example 3.3b. network route, and when you are not giving any number here, static route, by default, what number they are taking as a AD value? They will take number 1. So we have seen this. Let me go back. We have checked this AD value numbering, and here you can see that for directly connected host, the AD number is 0. That is the highest trusted. The trustworthiness, as you go low, the trustworthiness will increase. So this is the highest. Then a static route having AD1, EIGRP 90. Now these are the default values, right? These are the default AD value. That doesn't mean that you can't change it. You can make EIGRP AD value 150, 160. You can change these AD values. You have these tunable options in the protocol that you can log in, means you can go to the protocol and you can change the distance. You can change the AD value. So here you can see the concepts of floating route, floating a static route, that by default it is 1. You can make this more than 1. So suppose I am learning the route via EIGRP whose AD value is 90. So what I can do here, I can go here and create one backup route and make the AD value 91. So that means the 90 will be preferred. If 90 is gone, then it will start learning the routes via 91. Right. So these are the concepts that you can see here we have, and mostly we have done the lab related to this. Let's quickly go and perform the lab related to IPv6. Last time we have done lab related to IPv4. Why not? Let's do the lab related to IPv6. So let's go here and see the topology that we have. And then I will do show IP route and I'll show you that the AD value, that you can see the AD value and then the metric. AD value and then the metric, right? So this is normal static route. This is floating a static route. You can see the AD value is 200, and then you can see the default route. Default route will be S and then asterisk. Asterisk means default. So you have default route pointing towards the gateway. Likewise, you can see the IPv6 routes as well. So let's pull the lab server and let's perform the task. You can see that in the lab we have such type of connectivity. So I'm going to use the same connectivity, and what we'll do, we'll go and create a static route in between switch 101, router 11 and ISP, like here, a static IPv6 route, because last time we have discussed about, we have done a small lab related to the static IPv4 route, and I'm going to use such a schema. We are in router 11. Okay, so let's pull the server and let's do this. The devices, I can go to 101. 101, how it is connected to switch to router number 11. So this is connected over the interface E00. So I can go to interface E00. I can enable IPv6. Even before starting IPv6, you can go and use IPv6 routing. Make sure that your IPv6 unicast routing, yeah, that is enabled on the devices. And then we can go through interface E00, IPv6 address. I can go and start with 2001 DB8, right? And you can see the chart. According to that, you can go and create the schema. DB8, since one, you can see 1:::. Since this is switch 101, so I'll go and use 101/64, right? And then I will go to the switch, the router 11. Let's go and do that. Say IPv6 unicast, then interface. Here we have interface E0/3 that is connecting with switch. And here we will enable IPv6 enable. And then the address we can give 11/64. Why I'm giving 11? Because this is router 11. So I'm using 11. and this is switch 101, so I'm using 101 just to understand this naming convention and all. So once we have this, then we'll try to ping. Let's try to ping from this router, try to ping to the switch. You can see we are successful. Now from this router, I have one interface that is going towards the ISP, that is interface E0/0. And here also we can go and use IPv6 enable and then IPv6 address towards the ISP what I want to use. So let's see the address towards the ISP as per the schema. Let me go to the IP schema that we have. IPv6 schema towards the ISP. Even towards the ISP also I'm not using any specific different type of IP address. I can start with this like this and use it, no problem at all. So let's go and use the IP address this towards the ISP with this CIDR value /126. Okay, no problem. Let's do this. So towards the ISP, I just wanted to see this IP as well. Okay. 2001 colon DB8. Maybe you're unable to see, but I'll show you that 0:1/1/126. Let me show you this. So this IP I'm using towards the ISP. Then let me go to the ISP R3. It has interface, oops, it has interface E00, but let me do IPv6 unicast routing, enable this interface E0/1, and then IPv6 address, oops, you can see duplicate address. IPv6 address will be 2 here. And then from this, I will ping to 1. And you can see that we are able to reach, right? That we are able to ping. So we have this IPs that is assigned to the interfaces as per our IP schema topology. You can follow this IP schema topology just to be aware about the interfaces, how they are connected. That is there in the topology. And then you can configure these and you can practice it, no problem at all. So far what we have done, that we have created the IP schema, IPv6 schema, that will go from the that has the IP connectivity from the router 11 to router 3. Router 11 is my border router, and then router 3 is my ISP router, right? But can I reach from switch number 101? So we have switch 101 to router 3 IP. That's the thing that we have to create, right? So if I go to switch 101 and try to reach to the ISP router, this is what? This is the router number 11. So if I go here and try to ping to router number 11 or ISP router, it will not reach. Why? Because we do not have the specific route to reach to the ISP. So see, the topology is like this, that we have 3 routers. Router number 3, router number or switch 101. This is switch 101. So S101. Then we have router number 11. And then we have router number 3. That is your ISP router. We have IP addresses here. So from switch 101, I can ping to router 11. From router 11, I can reach to router 3 via the IPv6 addresses. But to reach to the destination network, right? To reach from here to this network, you need to get a static route that will go hop by hop, point by point. So let's see, let's try to create that. Let's see that how we can do that. Yeah, you have any query you can ask?
I have one. On the router 11, so you are doing a prefix 126. That is because if I get it correct, it's because it's a point to point.
Yes,
You
yeah,
you don't,
point
yeah,
to point.
right? You,
Yeah, that's why, yeah. So
okay.
point to point link, we can protect the IP addresses and we can create a specific IPv4, IPv6 addresses. That's why, yes, you're right. So in
Perfect.
OSPF, I'm going to explain about the point-to-point network as well. We have an example related to point-to-point network. We'll discuss about that. All right, so what we can do now, we can see that I can go to router number 11 and I can point this network towards the ISP. Maybe we have some little bit different IP schema and this is little bit different. So the IP that we have created, so let's do this. Let's go to the router number 11. So anyways, router 11 can reach to router 3, right? So there is no problem reaching to this. This is actually a specific route that is behind this, behind the switch. Router number 11, yeah, what I will do that for router number 11, I will go and create the default route. Default route. So where is the default route? Let's see. The first one, the first example. Yeah, this I will do. This route I will go. So let's do it. Let's do it step by step. So I will go to router number 11 and I will create the default route. How it is IPv6 route. And what was the 0? You can say this colon clone slash 0. That means everything. Double colon 0. That means 000. This colon means what? 00000000000 like that, you know. In IPv6, if you divide the addresses, 128 divided by 16, that means 8. So these is 8 consecutive zeros, 0000000 like that. And then slash 0 means again 128 zeros, right? And then the gateway. So who is my gateway from router number 11? This 2 is the gateway, right? Because you are able to ping to this, you are able to reach to this. So now if you can see, do show run section IPv6 route. So you have this specific, you have this default route, actually not a specific. You have this default route created towards the ISP, correct? So this is okay. Now how switch number 101 will reach to R3? So for switch number 101, we have to create the network specific route, right? So for that, we'll go here and create IPv6 route. And then I need this information with what? Slash 126. And what is my gateway? So my gateway 2001, DB8, right? DB8, and then what's the IP we have assigned to our interface? DB8 colon 1, 101, colon 1, colon 101. That means the router will be 11, right? This will be my static route. You can see if I have to go and create a specific network route, I want to reach, for example, I want to reach to this, then this will be the gateway that I have. In my case, IP is little bit different, so you can see the difference because this is what? This is the router 11 IP that is reachable. So via this next hop or via this gateway, I want to reach to the ISP, right? What's the IP to that ISP? So let's try to ping to the ISP and do ping and give the ISP address. This is the router address and this may be the ISP address, because it don't have the return route. So maybe that's the reason it will not print. So let's do that. IPv6. So last time I told you that when you're creating a static route, you should have entries in both directions. That's the inherent issue with the IPv6 addresses. So when I'm going in this direction, I should have some network coming in the reverse direction as well. Otherwise, they will not reach. So just for this example, I'll go here and I'll create IPv6 route and towards the gateway. My gateway will be the router gateway. And then if you try to ping, see, it is pinging and see it is pinging. So now you can see that our IPv6 static route is working perfectly fine, right? Likewise, you can work in your lab setup. So it is working, and I have explained you about all different type of routes that we have. We have the default route, we have the concept of network route, we have the concept of host route, we have the concept of floating static routes. Now, since we know the problem that we have with the static routes, the problem here we have with the static route is that the static routes, you have to go and create the manual entries in both the directions, in right to left, left to right. So for that, you can go and create the dynamic, you can go and use the concept of dynamic routing. And we have to learn one of the concept here related to OSPF version 2. OSPF version 2 means OSPF for IPv4 addresses. So you have to understand OSPF, how they are forming the neighbors, what is point-to-point network in OSPF, what is broadcast in OSPF, what is the use of router ID in OSPF, right? So these concepts we have to learn. Now, since this is a dynamic routing protocol, so you can go to the routers. It's actually very easy. You can go to the router, you can enable OSPF, router OSPF1, and this OSPF, they are very much area specific routing protocols. And then you can go and advertise a network 255.0 area 0. You have to define the area 0, area 1, area 2, area 3. It is area specific protocol. Then what you need to do, that you can go to the interfaces. Say interface is E0/0, and then you can advertise IP OSPF1 area 0. So those interfaces will be part of OSPF area 0. Maybe your interfaces will be part of area 1 as well, 2 as well, etc., etc. So you can assign those things to the interfaces. Even the point-to-point network, you have to go and configure over the interface. So configuring these type of routing protocols are actually very easy, because it will take care all the networks, their advertisement, their best path, because behind the scene they are running some algorithm. For example, OSPF, they have the SPF algorithm, shortest path first algorithm, which is running, and depending upon the link cost, they are selecting the best path to reach to the destination. This thing we have discussed in our previous session as well, when we are checking about the routing entry. So we have one routing entry for example, OS stand for OSPF, and then 192.168.1.0, and then you will see 110/40, and then you will see via 192.168.1. Or maybe 10.1 like that. So this is one of the routing table entry we have. Now suppose you have this entry, and after that you have this entry 192.168.1.0, same thing, 110 and then slash 90 via. So which particular routing entry will be preferred? This why? Because OSPF is working on the basis of cost, and cost here, this is what? This is your metric value. So in OSPF, cost is the metric value, right? So since the metric value here is 40 and here the metric value is 90, that means this will be preferred. Like that, OSPF, they are running their SPF algorithms and calculating that which particular path having low cost, and then that particular path will be preferred. Now this cost that OSPF is calculating, they can calculate this cost basis on the link bandwidth, but this is the tunable thing. You can go and change the cost value manually as well. So I can go to OSPF, I can go and use command IP OSPF cost 10. I can go to this interface and I can give IP OSPF cost 1, IP OSPF cost 20. So these things you can change, means you can traffic engineer your path. By default, your protocol will calculate the best path, that this is the best path, I should go via this path or this path. But we can go and tune as well. We can do some traffic engineering as well to manipulate our best path. Suppose I want to send the traffic via this path. So I can select that, right? So those things are there in OSPF. Now in CCNA level, you have to learn, understand this OSPF, only these items like how OSPF, they are building the neighbors, how they are what is point to point, and DRBDR selections and router ID. These concepts we have to understand. So let's understand this one by one. Neighbor adjacency. You can see I have switches and routers. Suppose if I go to these switches, switch 101, 102, 103, if I go and enable the OSPF protocol, let's focus on 101. If I go here and enable OSPF, then it will send that OSPF information to connected neighbors. So if all these three devices which is connected with switch 101, right, that will be the neighbor. That will be the neighbor for switch 101. Like that, this will work, right? So if I go here, switch 101 and router OSPF1, enable the protocol. I'll not advertise any neighbor here, but if I know the interfaces where I want to run the OSPF, so for example, uh, interface range, say loopback 0, E0, I know that we have interface 0001, these two interfaces that is connected with the routers. So interface E 0/0 and E0/1, I can do IP OSPF 1 within area 0. Likewise, I can go to switch number, okay, no problem. Let's go to router 11 and router 12. Router OSPF 1, then interface range. I know that we have interface 00. Let's start with loopback 0, E0/0. And I can take this as well. 0/0, 1, 2, 3. IPOSPF 1 area 0. And then I can go ahead to router 11, router OSPF 1, and then the interface IP OSPF 1 area 0. Now once you do this configuration, You can see we are getting one information loading to full. Do show IP OSPF neighbor. Clearly you see that router number 11 and router number 12, they are my neighbors, and you can see the state is full. OSPF having some states, the state is full, and this is BDR, DR and BDR, designated router and border designated router, that it is showing. Now if I go to router number 11 and if I run this command, you can see that they are the DR, they are DDR. So for router number 11, I can see switch 101, 102 and router number 11 because they are connected, and switch 102 also OSPF is running by default. So you can see that they are the DR, they are the DR, they are the BDR. DR and BDR selection is happening where you have the primary router, where you have the backup router, backup designated router, and primary router. We'll discuss about that. Here I just wanted to show you that you can go and see the neighbor information, show IP OSPF neighbors in detail. Even if you want to see the neighbor detail information, it will give you the neighbor detail information, right? So that's the way that OSPF, you can go and enable the OSPF. So here we are enabling the OSPF within area 0, but you may have area 0 connected with area 1, area 2. So in that case, area 0 will term as a backbone router. So here you can follow the IP schemas. Then you
But
can.
next question. What is the difference between area 0 and the other areas?
What is the difference between?
The area 0 and the other areas. Why
Yeah,
we
area 0.
most of the
Okay,
time they use area 0?
I'll explain that. Any other question you have? All right, so let's understand this, that how OSPF is working. 1 second. Okay, I'll explain here. Let me draw. So OSPF is designed to provide dynamic routing configurations. Means you don't have to go router by router, one by one manually, and you have to go and assign those networks and all those information statically. Rather than you can go use OSPF, ISIS, EIGRP, those dynamic routing protocols that will solve the purpose, and they will advertise the network, they will receive the network dynamically. These are the dynamic routing protocols. Now, when we are creating these dynamic routing protocols, there may be chances that your network domain will grow. Your network domain will grow. That means that your routers, number of routers will increase. Your business will increase, your number of routers and number of switches will increase. So according to that, what you need to do, that you need to go and run these routing protocol. But the problem here is related to a scale. It's a part of design scale. That means if your routers, number of routers are increasing, suppose now you reach to 20 routers or 30 routers, and all those routers, they are exchanging some sort of LSA, link state advertisements. They are sending the network information, they are sending the router information, they are sending the other router information. Suppose if one side you are running OSPF, other side you are running EIGRP, you are doing some redistribution. So there are redistribution related LSAs as well. So they are sending, receiving the other protocol informations as well. Now, in broader perspective, if you go and put everything within area 0, Suppose all those information we have within area 0. So there may be chances of getting the flood of LSAs. Now suppose if something wrong will happen with any of the LSAs, that will go and impact the LSA within the area. So within the area means that there are LSA that is specific to area. So on those design use cases, what we are doing, that we are creating OSPF in terms of hierarchy of area. That area 0 is my backbone area that is connected with different type of areas where I will further subdivide the routers. So in backbone, I may have 10-20 routers, but I will go and put 3-4 routers in area 10, 3-4 routers in area 20, 2-3 routers in area 30, and few other routers in area 40. So like that, I can go and divide the routers within the areas, because these routers within these areas has a lower LSA domain. So any flood of LSA will happen, that will happen only within these areas, that will not cross the boundary and reach to the core network. Otherwise, the core network will be injected with unnecessary LSAs. And the in terms of scalability, optimization, and security, that is not a good design. That's why within OSPF, we are creating a small areas that is connected with the backbone, and they are divided by the ABR routers. These are the area border routers. These are the area border routers. These are the ABRs, area border router. So from area border router, even you can go and create a stub. These are the design topics. You can go and create the stub. You don't want all the routes coming from area 20 to area 0, but you need summary route. You need default route. So you can optimize your routing table. You can improve the performance. You can enhance the scalability, right? And even you can improve the security as well. So that's why we are dividing the areas within areas, and everything is connected with area 0, that is termed as a backbone area. Okay, you got that answer?
Yes, thank you, Rakesh. I think that's a good explanation.
All right, so let's move to the topic here. The topic we have, that you can go and enable OSPF, advertise the network. Enable OSPF, advertise the network. Easy, straightforward, no issue at all. Even if you don't want to do this, what you can do, that you can go to the interfaces. So I can go to the interfaces that I have done in the lab. I can go to the interfaces, and over the interfaces, I can do IP, OSPF 1. 1 is nothing but OSPF process ID. You can give OSPF 1, 2, 3, 10, up to 65,000 numbers you can assign. OSPF 1, that's the process ID, then area 0. Area 1, area 2, it depends that what type of design we have. In my case, everything is running in area 0, so I can go and give area 0 there. Now in our case, there is one router number 11. If you see the topology, is here it is connected with router number 12, and they are connected with back to back. Their connectivity is back to back, so they are point to point network, and they are connected over interface E0/1. So if I go here and show run interface E0/1. So E0/1, you can see E0/1 having IP what? 252. Generally 252 we are giving. Why? In that case, you will get only two IP, dot 1 and dot 2. So if I go to other side, if I go to router number 12, so here you will see the IP will be 99.2. because we want to make this as a point-to-point network. So what I can do, I can go to interface E0/1 and I can do IP OSPF network point-to-point. Now, if you do network point-to-point, now we have network mismatch issues, and if you do network point-to-point, it's very interesting. And why they have given in this CCNA course, I'll tell you that. So I can go to 0, 1, I can make network point-to-point. And then if you do show IP OSPF neighbor, now you will understand the next topic. If your network is point-to-point, even they are not participating in DR-BDR selection. What is DR-BDR selection? I'll explain you. If network type is default, that is non-broadcast multi-access, NBMA, so they will do some DR-BDR selection. If network is point-to-point, then why they will participate in DR-BDR? So what does it mean? Let me quickly explain you this. So suppose this is our topology. Focus on this part. This is some sort of a LAN topology, or maybe let me go and draw some other diagram. That is some better example. So suppose I have one switch, and with this switch, I have router 1, router 2, router 3, router 4 selected. Now they are doing some sort of master and slave selection process in between them. So I have 4 routers, router 1, 2, 3, 4 connected with this switch. Now in this switch, they will go and do the selection, means in not this switch, but in this domain. So what I'm telling here is this, that suppose this is the should draw a bigger circle, all the routers. So this is one of the OSPF network I have, and everything is within area 0, right? And all these routers, they are running OSPF protocol. Since all these routers, they are running OSPF protocol, and they are part of same network because they are connected with what? Switch, right? That means they're part of, suppose they are part of 10.1.1.0. So router 1 having IP dot 1, router 2 having IP dot 2, it has having IP dot 3, it has having IP dot 4, right? So since all the routers, they are part of same network, we have to go and create some sort of DR, designated router, BDR. So who is the primary and who is the secondary in the network? Otherwise, what will happen? This is some sort of performance enhancement concept. Otherwise, what will happen? All the routers, they will send and receive the multicast packets from all the routers. Since this is the DR-BDR, if anything will happen in the router, if any query that router has to do in a network, then that query will send to the DR or the BDR, not to all the routers. You will send the query for any outage or any type of issues, any type of update. So that's why in a domain, we are creating the DR-BDR. So suppose router 1 is DR and router 2 will become BDR, backup designated router, DR and BDR. So these devices can query to DR. If DR is unavailable, then they will query to BDR about the network update informations. That's the concept of DR BDR. But think like this. But suppose in a network, if you have only 2 routers, why you will do the selections of DR BDR? No need, right? Because only 2 routers. So either this is DR or this is BDR or this is BDR, this is DR. Doesn't matter. So that's why you can see here in the point-to-point network case, use case, that there is no selection of DR BDR because that doesn't matter. So here you can see the state is full, but there is no selection of DR BDR. We are doing the selection of DR BDR only in case when you have non-broadcast multi-access type of network. In case of point-to-point network, it's not required. So here you can see that you can go and assign point-to-point network, it's easy and straightforward, and DR/BDR selection in a broadcast network. Yeah, in a broadcast network, or NBMA also, I think, non-broadcast multi-access network. You can go and create the DR/BDR to reduce the number of adjacency. Otherwise, everyone will go and query to all the routers, and then you can go and do that. Right? Means by default, routers will do that as per the router ID and the priority. They will do it because by default there is priority. But if you want that one of the switch will become the DR, means forcefully, if you want to do this election, then you can go and use IPOSPF priority command, and that particular switch or router will become the DR. So we can go and do it manually as well. The selection of DR/BDR selection can be manually with the CLI command as well. The last topic we have is the router ID, the use of router ID. So at the moment, we'll go and enable OSPF. Let's see the concept of router ID. Show IP route. Show IP route. Where is that router ID? Okay, let's see. Show IP OSPF neighbor in detail, and yeah, neighbor ID, neighbor address. Okay, show IP OSPF neighbor. See, when they are forming the neighbor, you can see the neighbor ID. Actually, this should be the router ID. I will explain you about this 1 second. Okay, let's see little bit. Let's dig little bit more about this. So, show IP OSPF. Show IP OSPF databases. So here we'll see that router number 11 having router ID 10.1.255.11. Show IP interface brief loopback 0. You will see that the loopback address. The loopback address is my router ID. So the selection process is like this. The selection process of router IDs are that first priority will manual command. Manually, we can give the command OSPF router ID and assign any router ID. Secondly, that will be the loopback IP. Third is the, suppose you don't have the router ID command, you don't have the loopback over the interfaces, so it will go and take the highest physical interface IP. So over the physical interface, suppose you have IP11, so okay, 12.12.12.12, or you have IP 14.14.14.14. So the router ID will be 14, 14, 14 because 14 is more than 12, right? If you have loopback, generally in the network, you will see that we are providing the loopback addresses. So if you have the loopback, in my case, I have the loopback configured as this. So that's why when they are forming the OSPF neighbor relationship, OSPF, show IP OSPF neighbors. So they are using the loopback addresses to form the OSPF adjacency. That is one of type of best practice that you can go and use create the loopbacks in your routers, and with the loopback, they will automatically form the neighbor relationship. But in case you want to force, you want to use your router ID number, so then you can go and use this command, and forcefully it will work. So if I go here and if I go to router OSPF 1, say router ID, but once you do this, it will ask you to clear the process, clear IP OSPF process. So now your OSPF will restart and it will rebuild the OSPF neighbor table, topology table, and routing table. First of all, they are building the neighbor table. With help of neighbor table, they will go and build the topology table or the database entries. And then finally, it will go and build the routing table. So there are process behind the scene. First of all, these OSPF, they are building the neighbor table, and then they are building the topology table. It's nothing but the database table. And then finally, they are building the base path, that is the routing table. Neighbor table, how you can see, show IP OSPF neighbor command. Topology table you can go and see, and all the LSAs you can go and see. Show IP OSPF database. And finally, the routing table, you can go and use show IP route. Even you can filter with OSPF. Show IP route OSPF will give you the routing table. So now we have done that. Now if you go and see show IP OSPF neighbor, you will see that the router ID should get changed. So if I go to other router, show IP OSPF neighbor, you can see that learning this with 1111, because we have forcefully changed the router ID to 1111. Right, so these are the concepts that we have to understand in the OSPF, and we have completed day number 11. If you have any question, please feel free to ask. Thanks for joining. Day number 12, we are going to learn about first hop redundancy protocol. Anyone knows what is first hop redundancy protocol, why we are using it?
No, I don't know. What is that?
Okay, no problem. This is one of the redundancy technique that we are providing in a network. So if you go and check our topology, we have distribution layer switches that is connected with access layer switch, and this access layer switch is connected with different type of PC server, etc. So if I go and draw the topology, so topology is like this, and then you have aggregation, like multiple links bundled together, and it is connected with the uplink. Uplink means that it is connected with the distribution level switch, like this. Even we have back-to-back connectivity, back-to-back aggregation in between the distribution switch as well. So if I go and name this is switch number 110 in our diagram. Then we have switch number 101, and we have switch 102. Now we know that we are creating some sort of VLAN. So maybe VLAN 2000, 2001, or maybe VLAN 10, 20, 30, oops, 20, 30, 40, etc. These VLANs we are creating where? To the access switch, right? So suppose one of the PC is part of VLAN 2000. and other PC is part of VLAN 2001. One PC is part of 2000 and other is part of, suppose 2000, another PC is part of 2001 as a access VLAN, right? It can be, there is no problem. Few of the system, they are part of different VLAN, few of them are part of different VLAN. Now let's focus on VLAN 2000. Suppose you have PCs part of VLAN 2000, right? Now, how our connectivity is that we have one router here. The moment I'll take one router, and then you have connectivity like this. And this router is again connected with ISP router. So then you have connectivity like this, R11 and ISP. ISP where you have the WAN link, where you have the WAN link. Let me go and draw one more link here. Like this. This is your, assume that this is your WAN, wide area network link. This is WAN link. Okay, so these are your LAN facing interfaces. This is going towards the switch. So the interfaces that is going towards the switch, they are the LAN facing interfaces. Now see the use case. The use case is like this. So if this switch access PC, so if this PC that is connected with this particular switch, this particular PC has to go outside, it can go like this, right? Or it will go like this. How the traffic flow will happen? So it can either go in this direction or it can go in this direction. Both directions it can choose, right? But the switch will follow this path if you define the gateway to this switch, right? So it has VLAN 2000 and VLAN 2000, if it has go to the router and use some internet, right? So it should go via this path if you have the gateway defined here or gateway defined here, right? You're able to understand up to this part?
Yes, I got it. That part, yeah.
Right. So either it will go via this direction, but think that if something will happen with this switch and if this switch will go down or get a reboot or memory issue or CPU issue, high CPU issue, if this switch is not operational, then since you had defined the gateway to this particular switch, what will happen that the packets reaching here, after that it will start getting dropping because you have defined the gateway to this switch and this switch is down. Then how you can go outside? You can't go outside, right? Means you can't leave from here because you have defined the gateway here. You can't go like this. See, you have an alternate path like this. You can't go like this. You can go like this because anyways this is down. So you can't go like this or you can't go like this, right? So that's why we have technique called first hop redundancy protocol. Your first hop gateway. First hop means what? Where is your gateway? So what we are doing, that we are creating some sort of, we have some sort of protocol technique that the switch 101 will be my primary and switch 110 will be my backup. So now we have concept of primary and backup. Now, if anything will happen with primary, if this is down, then backup will become primary. So that means the gateway, they will go and check that, assume that this is my gateway and I have to send the packet via the backup path, right? Via the this switch. So in that case, you will not go and give the, so for, let's see one more thing. There is some confusion. So suppose, let's write the IP addresses and all the things of this particular device. So suppose this particular device having the IP addresses, let's choose those type of IP addresses that we are going to use in the example as well. At the moment, I'll type anything. So 192.168.1.10 is the IP, and the gateway 192.168.1.1, right? And gateway subnet mask 24 255.255.255.0. Now this 1.1 you have defined here, right? Oops, color is so faint. Okay, let me use black color. So this gateway address 192.168.1.1, you are defining where? You have defined here. So if this is down, if switch 101 is down, that means traffic will get black hole. It will not go anywhere, right? So what we are doing, that we are not using this technique, but we are assigning some other IP to the switches. So for example, the primary switch having IP 192.168. Suppose 1.10, and the secondary switch has IP 192.168.1.11. But what we are doing, we are creating one ghost IP, one virtual IP, that will be 192.168.1.1. And that ghost IP that we have, that virtual IP that we have, it will be glued with this also and this also. So this device do not have switch 101 IP, switch 102 IP, but it has some ghost IP. In FHRP term, that is the virtual IP, VIP virtual IP. That ghost IP is nothing but the virtual IP. And this virtual IP is glued with this interface also, or this IP also, this IP also. That means that if this switch will go down, the traffic can go like this. If this switch is up, the traffic will go like this, because as per the protocol, this is the primary and this is the backup, secondary.
That primary and backup is the same as we saw yesterday, the DR and the BDR, or there are two different
like that. So
yeah.
we have protocols here like VRRP, standby, hot standby redundancy protocol, GLBP. Like those, we have protocols that we are going to learn. But overall, this is the concept. So let me go here.
Okay.
FHRP, first of redundancy protocol designed to provide high availability and redundancy on the for the default gateways in a network. They ensure that the gateways are always available for the host. It will provide you redundancy, high availability, load balancing. What they are doing, so they have some concept. They have concept of virtual IP and virtual MAC addresses. So not only the virtual IP they have, the IP that 1.1 you have, it has some MAC address as well. So that MAC address associated with 1.1 will be the virtual MAC address. And then we have concept of active standby, active and backup. We'll see that active standby. Then you can define the priority. See, with this priority, higher is better. With this priority, we can make one switch as a active, one switch as a backup. And there may be cases, there is one use case here. Use case means that this is the topology that we have. Now think here, oops, that what if, that if this switch will go and reboot, If this switch will go and reboot, then this will become active, right? But if after reboot, if it will come back online, then still the traffic is going via this direction until unless you will go and use the command called prompt. If you run the prompt, then they will maintain their state. After reboot, you can see preemption. This is the feature allows a router with high router ID to take over as the active router when it become available. Means once the active router, once the primary router will come back online, that will become the active again after reboot, after any failure. What is the
That
protocol?
will be happen dynamically, or you have to do it
Dynamically.
manually? Okay.
Dynamically. If you do this preemption dynamically, it will come back.
Okay.
We'll see that, no problem. So here you can see that we have the protocol supported HSRP, VRRP, GLBP. HSRP is Cisco proprietary, GLBP is Cisco proprietary, VRRP is industry standard. So what is it? HSRP, hot standby routing protocol. They have the mode active and standby, and they are sending the hello package just to check that who is the active, who is the standby. Then how we can go and configure it? Its configuration is very easy. You can go to the interfaces. Either you can go to the interface, physical interface, or you can go to the VLAN interface, like VLAN interface, VLAN 2000 interface, VLAN 2001, and then you can give what is the gateway address, what is the priority, and the prompt, like these three commands. And then with this higher priority, switch 101 will become the primary, switch 102 will become the active. Like that, they will choose the, they will do the election. Then we are happy. So concept is the same. Configuration here, instead of a standby, you can use the keyword called VRRP. Then instead of the VRRP, you can go and use the keyword as GLBP. Right? Even in GLBP, we have concept of active gateway and the active forwarded gateways. In GLBP, this is nothing but the load balancing as well. This is the only protocol that can do the load balancing as well. I'll come back to GLBP. Let's first go to standby and then VRRP, because both are almost same. The difference here is that VRRP is industry standard. It is supported by non-Cisco devices as well, like Juniper and other vendors. They are supporting VRRP as well. And other thing is that VRRP, we can go and tune the timers as well. In other hand, HSRP timers are a little bit slow. So generally, you will see people are using VRRP in their network. So let's go one by one. Let's go with a standby first, and then we'll go to the VRRP and then GLBP. Let me pull my server here, this lab devices. We know that these lab devices, 0/ switchport mode access, switchport access, VLAN 2000, and this is the access switch. Here you don't have to do anything. These are the VLANs we have. Let's see the IPs that we have on this. Port channels are down and all those things, right? So I need to go and do some default and remove the port channels. It's not necessary, the port channels, although you can configure the port channels as well. But anyways, for the simplicity, as per the diagram that we have, let me go to the diagram. Just follow the diagram that we have here. Where is the diagram? I haven't attached the diagram here. The topology. That is there in OSPF section seems. So let's go back. Here it is. So you can see the interfaces, right? I'm going to use the interfaces like one interface because my purpose is to create the uh, HSRP, hot standby routing protocol configuration over these switches VLAN interface. So for that, I will do the configuration. So here I'll go and remove those unnecessary configuration like no interface port channel 1, port channel 2. Then we can go and do the default for interface E 1/0, 1/1, 0/1. Oops, not 0/1. 0/1 is mode access. 1/2 and 1/3. Let me go to interface E0/1, switch port mode access, and switch port access VLAN 2001. Now let's do quick configuration to these devices as well. Here also I don't have no interface, port channel 1, port channel 2, whatever port channels it has. And then we'll go and do the default for interfaces E1/2, default for interface E1/2, E1/3. And likewise, I can go to 102 as well. And no interface port channel, INT port channel 1, port channel 2, port channel 3. And then default the interface for E1/2, 1/2. Now these interfaces that we have, so suppose first of all, you should go to the interface E1/, or you can go here and check this. Do show interface E1. Make sure that they are not in the ports are not in the down state. There will be something called error disable mode. There may be chance that they are in the error disable mode. So make sure that they are not in the error disable mode and you are learning. So you are learning this. I can see router 11 and router 12 in 101, but I'm not seeing switch number 10110. Switch number 110 is not there. So we should see that. Otherwise, that means that interfaces are down. So what we can do here is this, that we have to go and configure the VLANs. So the strategy here is this. See, you have one switch. Let me try to draw here. So I will show you the strategy. Just focus on these three switches. Now these three switches, and you have like this connectivity like this. Here we are making switch port mode access. Then what we'll do, we'll make these interfaces a trunk. These interfaces will make as a trunk, right? Trunk. And then here also we'll go and create a VLAN 2000 and 2001 over these switches. Since these are the trunk, so they will pass the VLAN. And here the interfaces are part of 2000 and 2001. So that's the strategy we are going to use here. So the interface that I have connecting in between the switch, say interface E1/0, switch port mode trunk, switch port trunk encapsulation.1q, switch port mode trunk. I can go and take these configurations. Switch mode trunk encapsulation.1q, switch port mode trunk, interface E1/2 on the other side. Then I can go here. This is connecting with the switch 110 over interface E1/2, interface E1/2. Right. This is also good. And there also we'll go to the interface E1/0 and interface E1/2. So what I have done actually, that you have the interfaces, you have interfaces such as E1/0, and here you have E1/2. Here you have E1/2, and here you have E1/. So these interfaces we have make as a trunk, and here you have E0/0 and E0/1. Here we have made as a access, right? Now make sure that all these switches having the VLAN 2000 and 2001. Now before that, I should ping to in between the switches. So I can see that VLAN 2000 they have, and they have VLAN 2001, right? They have the IP which is up. Likewise, if you go here and see the IP address, you can see VLAN 2000 and 2001. What's the IP? 10.102, 10.1.1.0.1.2, like that, right? So if I go to this switch, my access switch, make sure I'm able to ping. It is telling this is the unrecognized, and since this is the access switch, we are unable to reach it. It is not necessary that you can go there and ping, but you should have the VLAN. So I can see that we have the VLAN 2000 and 2001, right? So you have the VLAN 2000 and 2001. Likewise, make sure that you have the VLANs. So you have the VLAN 2000, 2001. So now we are ready. Now we are ready means the lab is ready to do the HSRP configuration, hot standby redundancy protocol configuration. Up to this point, if you have any query, please feel free to ask.
No, I think I'm good.
All right.
Completely.
So let's do the HSRP configuration, and then we'll do the testing as well. Okay. So we are in switch 1. You can go to interface VLAN 2000, right? And then use the keyword standby, and then you have to give the group name. So group name may be a type question. You see, the group number should be in between 0 to 255. So suppose group I will give 100, and then it will ask you the virtual IP. So IP will be virtual IP, and we can go and use say 10.100.2 is there. So I can go and use 100.1, then a standby 100. Then you can go and use the command called print, then standby 100. We can go and give the priority, for example 110. Default is 100. We can go and give the priority 110, right? Apart from that, there is one option called track. For example, track give 50. What this track is doing, that you can go and monitor the uplink as well. So I'll show you that what this track is doing. Where is my, okay. Second, you can see the diagram. So see, track, I'm using track of 50. So with HSRP, what will happen that it will monitor either this device as a gateway, this device as a gateway, right? Now, what about the uplink? Can you monitor the uplink? Can this PC can see the uplink? No, right? They can't see the uplink. So if this uplink is down, you can't go like this, right? You can't go like this if this is down. So if you go and use track of 50, that is something you are monitoring the uplink. So suppose if you are not able to go like this, what this tracking command will do, that from 110, suppose its priority is 110 and this priority is 100 by default. So 110 minus 50, and if it is not able to send the packets in this direction, it will decrement the priority to 50. That means the priority will become 110 minus 50, that is what, 60. So now its priority is 60 and its priority is 100. That means the traffic will go like this. What the point? Using of track. We are using the track to monitor the uplinks. All right. So let's go and pull this server. Okay, so
What
we
happen if you have the same priority on both the switches? That will trigger an error, or what would happen there?
so they will go and choose one of the gateway as per the lower IP addresses over the VLAN interface. So VLAN interface having IP like this and other having IP.3. So as per the lower IP address, they will choose the switch 101 as a primary. Okay,
But
let's.
it's not recommended, like best practice, not
Yeah, means you
to.
should give the priority. So you should know that which is your primary, which is your backup, like that. So we are giving the priority. We are making one switch as a active, one as a backup. Right, 100 framed, and will not give the priority here because by default priority will be 100. So now if you go and see here, we can do this thing, no problem. You can test it. Show standby brief. So now you will see that within VLAN 2000, group is 100. Priority, you can see priority is 100. So what is the state? State is the active, and who is the active? The primary one is the active, and then you can see that is unknown, that they are not sending, receiving the packets. It will take some time to get converged. Now this is good. Do show a standby brief. Now this has some split brain scenario. Both they are not exchanging the packets to each other, and they are thinking that both are active. Once they will go and sync, then one will show as a active and one will show as a standby. So let me go here and let me do one thing. I should go and make E2/0. Let's make this default interface E2/0. E2/0 switch port trunk encapsulation dot switch port mode trunk. This interface that is back-to-back connection, that also I'm making as a trunk. Default interface E2/0 switch port mode trunk. That's to make sure that the messages they are passing to each other. We show interface E. Let's check the interfaces E2/0. What's the status? They should not be in the irreducible. Oh, it's down. Shut. This interface was down in between them. They're bringing that interface. And I will wait till our standby will come into the picture. So let's go and show standby brief. This will become the other switch. So now in the output, you can see that what's the group ID, what's the priority, what's the state, I am the active one, I am the local, and then you can see the VIP IP. At the moment, switch 101, now you can see the priority got changed. You can see the standby is who? 102. Now 102 become standby. Why? Because its priority is less. So if you go here, now you can see that it is the standby. If you go and see this, show standby brief, brief, standby is local. Why? Because its IP address is .3. But both the devices, they are telling that their VIP is this. So where you will assign the VIP? You will assign the VIP to the PC here. So let's go to one of the PC which is part of VLAN 2000. So this is the host actually. No IP routing. We'll make this as a work as a PC for the testing purpose. What interface it is connected? It is connected over interface E0/0 192. So this should have the IP address in the same range, right? 10.1.100. For example, 10, right? No shut. And then see the default gateway will be 10.1.100.1. This default gateway is the gateway for the VIP IP. Now, if the connection is correct, it should go and reach to that VIP. Not reaching to that VIP, maybe in between some of the interfaces are not working. We will go and check that. So let's go and do the checking. I'll go and check the interface E1/2. Show run. Show interface E1/2. It should be up, connected and up. Great. Then I will go to switch 110. Interface E1/0. It should be up. Say line protocol disable. E1/0. Shut. No shut. It is coming up likewise. Interface E1/2. Shut. No shut. Now if I go to the host, let's try to reach to the gateway. Not reaching, no problem. We'll make that reachable. So what we have done so far, you can see that we have created the HSRP. This is the primary. Switch 101 is the primary, and this is the backup. So the traffic should go from the access switch to this switch, and then it should go outside, right? Because this is my gateway. So the PCs that we have here, the host that we have here, we have provided the gateway. This is the gateway 10.1.100.1, right? Now to reach to this gateway, this switch should also reach 10.1.100. Since switch is not reaching, it has some issue. I'll do one thing. Interface VLAN 2000. Interface VLAN 2001. Interface VLAN 2000. I need some IP here, not this IP, but I need some IP here. For example, 100. And this is the VIP IP I'm paying. Virtual IP, right? Now from here it is reachable. And can I ping? I can see. Able to reach to the gateway, which is the VIP gateway, virtual gateway, right? Now, what we can do here, that um, count for um, okay. So now what we'll do here, we'll go to this switch. Reload, right? Yes. Confirm. You can see that this switch is down, making this switch as a reboot package. So then in that case, it should go and, because this is VIP IP, so it should go and ping to this, right? Because in that case, the active will become a standby will become active. So that means if I go here, now they are doing the election process, seems state is unknown. See, state is unknown, it is taking time. Now you can see who is active. And if you go here, you can see the ping is working. So there are, let me stop this ping. Oops, I'm unable to stop the ping, but you can see some drops. And what happened now, that the standby is becoming active. This is active. Who is active? So after reboot, maybe it is back. So see, after reboot, it is back, and now again it become active. Why? Because you have done the print command. So earlier, you can see active. It become active, and then again it is standby. So that's the thing they will do. You know, that's the thing, because we have done the prim command. So the active will become again the active. That's the process they are following. Any question in this? Please feel free to ask.
So using the priority, what will be the case of not using that prem configuration? Like why not use it?
Sorry,
Or why
what?
someone will manually change the the backup or do the active to the standby instead of doing dynamically. You know?
So we are not doing this manually, right?
Yeah,
Dynamically,
I know.
dynamically they will
I
change it. Yeah.
but my question is, you can do it manually, right? Also.
Manually also you can go and change the active to backup,
Uh,
backup to active. That's right.
and what will be the case of using a manual process?
Manually, why we are doing this manually? They are not taking my CCNA classes, so that is maybe one case. No one is doing no one is doing like that. Means we have one option, and it's up to us that we are using that option or not. So maybe one case maybe that people they don't want to have one more flap. So what is happening, that this switch will get reboot, right? If this switch will get reboot, then what will happen? You have other path. Generally, it is happening in a network world that if something is working, do not touch it. So if this switch is down, that means you are going via this direction. So after one flap, network will get flapped, right? Because there is timer, like 3 seconds, 10 seconds, they will go stop sending the traffic until it will become the primary, and then the traffic will go like this. So there are chances that this switch is flapping, like, going down, coming up, going down, coming up. It has some issue, some high CPU after every 5 minutes. Then what will happen? This will become active and traffic will go like this. And once it will come back, again traffic will go like this. Again it will go down, the traffic will go like this. Again it will come up, traffic will go like this. So you will see outages in network. If
Okay.
the if this switch having such issue that after every 5 minutes it just stops sending traffic. So in that case, this automation will not work. So you will not want that the preempt is there. Preempt is good if both switches are stable and you have rare flaps, rare reboot. If one of the switch is disturbed like all the time, even the interfaces are not working properly and it is becoming active. So those cases you don't want to use the preempt,
Okay. Got it.
right? Okay, all right. So now we understood that how this HSRP is working. Why not we'll go and configure VRRP. So let's do that. So I can go here to the same switch. And we have one more VLAN. Say VLAN 2001. Here I can go and use VRRP. Suppose 101 IP 10.1.101 is the VIP IP. VRRP 101 preempt VRRP 101 priority. Same configuration you can see. Same line of configuration. Oops, we are doing here preempt and priority when we don't need priority on the other switch. Now once you do that, their timer are very fast and one will become active, one will become a standby. Show VRRP brief. So now you can see that one is master. Master is master. And if you go to 10 VRRP brief, you see this is the backup. So one is the master and one is the backup, and the scenarios are almost the same. Same way they can go and react. Now there is one more option we have is related to GLBP. So let's go and do that. So I'll go to interface VLAN 2001, sorry 2000, and make this no standby 100. I'll remove that, a standby brief. Likewise, I'll go and remove this configuration from 101 as well, interface VLAN to the, because this time I want to run the GLBP. So we are over the interface 2000, and we will go and use a GLBP 100 IP 10.1.100.1, GLBP 100 preempt, GLBP 100 priority, suppose 110. We'll go and copy this GLBP and we can come here and then we'll do show GLBP summary or brief. So now you'll see interesting output here. GLBP. In GLBP, we don't have the active, but we have the backup as well. So if you go and check the GLBP, let's go and check the theory here. So if you read the GLBP, let's go back to GLBP where it is. Oops. close this. Okay, so here you have the GLBP. In GLBP, they can do the load balancing as well. They have two gateways. One is active virtual gateway, assign virtual MAC address to other routers. One is active virtual forwarder. This is actually the forwarder, the gateway, sends the traffic. And hello packet will be exchanged in between to sync the traffic, right? So in our case, you can see that within VLAN 1, one is the active forwarder and one is the listener. This is working as a backup, right? So in we have created this group. In that group, I can see that we have the forwarder. See the forwarder 2, which is active, which has the virtual MAC address. It is the local. Oops. Do show. Let me see GLBP. Brief. This should be the primary one because yeah. So here you can see that this is the active. Now the thing you can see that both switches are active. So this is active for number 1. You can see for number 1, and this is active for number 2. That means both are sending the traffic. So point here is this. With this protocol, point here is this, that at a time both the switches, they are forwarding the packet this direction also, this direction also, because in the output you can see that both are active. This is also
Also,
active.
they share the traffic, and
This is
it is
also,
like they are sharing the traffic, both
yeah.
both routers. Okay.
You can use the load balancing methods here. You can see that even we can go and choose the load balancing round robin, weighted, host dependent. Generally we are using round robin methods, so they can go and
Okay.
share the load across the switches in a round robin fashion. So that's the use we have with the GLBP. So now you can understand the HSRP, the VRRP, the GLBP. Configuration wise, it's not a difficult thing to configure it, right? But conceptually, how we are utilizing this, I'm going to give you a nice concept here. So instead, so people are not using GLBP because it has so many internal issues. So what people are doing, let me show you the design. So you have one switch, you have two switch, and one you have this switch, right? They're connected to each other. We know that we have VLAN, VLAN 2000. Suppose we have VLAN 2000, or we have group of VLAN and group of VLAN like that. So we have VLAN 1 to 100 and 100 to 200 like that. Assume that you have only two VLAN here. So instead of using GLBP, why not make, so for example, we are going to use HSRP, only HSRP or maybe VRRP. We are going to use VRRP. Why not for VRRP, use VRRP protocol? Why not for VLAN 2000, make this switch 101 as a active for VLAN 2000, and why not for VLAN 2001 make this switch as a active? So for VLAN 2000, the traffic pattern will be, for VLAN 2000, will be like this. But for 2001, the traffic pattern will be like this. So that will be active, right? If you see as a whole, for VLAN 2000, 2001, you will see that for 2000 traffic is going like this, 2001 traffic is going like this. That is possible, that we can do, right? So actually we are doing such type of methodology that we are balancing the load in between the VLANs. So what I'm telling here, I can go and configure as well. So I can go to this particular switch. I can go to interface VLAN 2001, VRRP group 101. Close this. 101, the IP, so 10.1.101.1, and then VRRP 101. Print is okay, but the priority here I will give, say for example 50. By default priority is 100, so if you give the priority as a 50, that means for VLAN 2001, this switch will be the active. Now if you go here and you do show VRRP brief, okay, I have removed the VRRP sims from VLAN. Go to interface VLAN 2000, no GLBP, the group name 100. Wow. I think it will remove. Okay, so we are here in the interface VLAN 2000, and here for 2000 I'll make this active. VRRP 100 IP 10.1.100.1. Interface VLAN 2000. What is there? Oh, GLBP is running. So we'll make this 100 and for example print, and the priority is 150 more. So I'll go to the VLAN 2000. Oh, no GLBP 100 and IP and print, and I think that's it. Now we'll see, do show VRRP summary or brief. You see, so for VLAN 2001, see here. So for VLAN, oh my God. What is happening? Do show run interface VLAN 2000. Why it is resolved failure? VLAN 2000. Some issue is there. I will solve that issue. Let's see. What we have done here, that let's see, do show run interface VLAN 2000. Okay, so 2000, we are making this as a primary, right? 10.100.1. That's right. That's right. Let's go here to 102. 2000. Okay. Interface VLAN 2000. We should give VRRP 100 priority. VRRP 100 rimmed. I'm getting some address resolution issue. for VLAN 2000. Agency address failed. Oh my god. And VRRP 100 IP is okay. 10.100.1. That's the VIP IP. Let me go and change the priority. Okay, so point here is this. Anyways, I will reboot these devices. It has some issue. It is showing some duplicate address issue. But if you go and check the VRRP brief, you will see that for 2000, this is the backup. For 2000, this is the master, and 2001, this is the backup, right? Likewise, in switch 102, VRRP brief, you will see that for 2000, this is the backup, and 2001, the master. So you can do like this, you can do like this, that for one VLAN, one of the switch is the gateway. For other VLAN, other switch will be the gateway. So you can load balance across the VLANs. That is always there. Instead of using GLBP, you can use such type of methodology. Okay, you have any question, please feel free to ask.